Hello, this is Mr. Mac. This is the second video dedicated to understanding the concepts of limits, and I need to do a couple of things before we can actually jump into the limit itself. The first thing I need to do is to talk to you all about solving absolute value inequalities. Now, one of the things that you were supposed to learn in Algebra 2, but it isn't done that well sometimes, is absolute value inequalities. And what I'd particularly like to look at with you is the absolute value inequality that looks something like this. The absolute value of x minus c is less than r. Now, let's start with a simple example. How about absolute value of x minus 2 is less than 3? Now, obviously, if x is 2, it's true, because if we put 2 minus 2 in, it's 0. Absolute value of 0 is 0, and 0 is less than 3. So if we were just, spitballing here, let's take a number line, and we'll put 2 here. 2 is going to work. Now, if I put in 3, 3 minus 2 is 1, and its absolute value is 1. That's less than 3. That would work. And if you think about it for a moment, it would be true for all the values between 2 and 3. So I'll just shade those in. Let's try 4. If we put 4 in, we would get 4 minus 2 is 2, and that would be absolute value of 2 is 2, and that is less than 3, so 4 works. And so the values between 3 and 4 would also work. And then if we put 5 in, let's just look at 5 here. If we put 5 in, 5 minus 2 is 3. The absolute value of 3 is 3, and that's not less than 3. So 5 doesn't work, but it just doesn't work. What about 4.9? If I put 4.9 in for x, 4.9 minus 2 would be 2.9. The absolute value would be 2.9, and that is less than 3. So the numbers to the left of 5, and actually right up to 5, will work. In fact, 5 is the first number that won't work. So ordinarily what we do is we put an open circle around that value. So if you look at this interval from 2 to 5 without including 5 works. Now, it's pretty clear that if we go past 5, like say if we try 6, the absolute value of 6 minus 2 is 4. That's not less than 3. That won't work. And any other value past 5 won't work in either. In fact, in geometry, when you're doing the ruler theorem, or the ruler postulate, you were taught that if these two numbers were coordinates on a number line of 2 points, maybe A and B, then the absolute value of the difference of their coordinates turned out to be the distance between the 2 points. And so if you look at this in the geometric way, what we're saying is the values, the points of who x is their coordinate, if their distance is less than 3 from 2, they would work. But if we look at that down here, then we don't have a complete picture of this interval. Let's try 1. See, if we put 1 in for x, 1 minus 2 is negative 1, but its absolute value is 1. That is less than 3, so 1 works. And I hope it's clear that the values between 2 and 1 also work then. And let's try 0. 0 minus 2 is negative 2. Absolute value is 2. That's less than 3, so 0 works. And without loss of generality, I'm going to claim that the ones in between also work. I hope you believe that. And then we try negative 1. Now, negative 1 minus 2 is negative 3, and its absolute value is actually 3. So negative 1 doesn't work. But just like 5, it just doesn't work. Anything to the right of negative 1, like negative 0.99, would work, because negative 0.99 minus 2 is negative 2.99. And the absolute value of negative 2.99 is 2.99, and that is less than 3. So negative 1 is the first one that doesn't work, but the stuff in here does, and then nothing past to the left, negative 1, would work either. So what we've really got is an interval from negative 1 to 5, not including the endpoints. But now what I'd like to point out to you is that the distance from 2 to 5 is 3, and the distance from 2 to negative 1 is 3. And so what we're saying here is that we want all the points whose distance from 2 is less than 3. Or what this makes this is an interval that's centered at this value and has a radius of this value. Now, if I wanted to make this interval smaller without changing where it was centered, all I would have to do is decrease the value of r. So you can see that this is a very useful tool if we want to talk about squeezing in or talking about the numbers around a certain number, but in other words, wanting to squeeze in and make the interval of numbers around that number smaller. And remember in our last video, we were talking about getting closer and closer. This is a mathematical way to do that. If we just take the x minus the value we're looking at and put it less than, and then the number here gives us the radius around which we're willing to allow you to look. Okay. Now, the next thing we need to talk about, because a little bit later I'm going to show you, I need to show you a function where it doesn't work, and I'd like to have this kind of in place already, is let's take a look at the function f of x is equal to the sine of pi over x. I can do better than that. All right, now, obviously, and we're going to eventually ask ourselves, what is the limit as x approaches 0 of the sine of pi over x? Well, let's look first at the graph of the sine of pi over x. We could do this with a table first. Let's start out with a few values. And what I'm going to do here is I'm going to start with 1, and I'm going to move towards 0. Now, if x is 1, then f of 1 is the sine of pi. Now, the sine of pi is 0. Now, as I move towards 0, I'd like to use 2/3. Now, f of 2/3 is the sine of pi divided by 2/3, which is the same thing as the sine of pi times 3/2, or the sine of 3 pi over 2. Now, if you think about your unit circle, the sine of 3 pi over 2 is -1. Now, the next number I'd like to look at is x equals 1/2. Notice I am approaching the 0 here. The f of 1/2 is the sine of pi divided by 1/2. But pi divided by 1/2 is 2 pi, and the sine of 2 pi is 0. And then I'd like to try 2/5. Now, the sine of pi divided by 2/5 is the same as the sine of 5 pi over 2. So the sine of 5 pi over 2 is 1. Now, let's try the sine. Let's try x equals 1/3. Now, the sine of pi divided by 1/3 is the same as the sine of 3 pi, which again is 0. Then let's try 2/7. Now, the sine of pi divided by 2/7 is the same thing as the sine of 7 pi over 2, which is again -1. And that was so much fun. Let's do 1/4. We get 0 again. And how about 2/9? We'll stop at 2/9. The sine of pi divided by 2/9 is the same as the sine of 9 pi over 2, which is 1. All right, so now let's take a look at what this graph is going to look like. Here's 1, and the sine of f of 1 was 0. Now, here's probably 2/3. And the value of that was -1. Here's 1/2. The value was 0. Here's 2/5. The value of that was 1. Here's 1/3. The value of that was 0. And then we go 2/7, which is going to be pretty close here. That's -1. And 1/4, probably here. We're back at 0. And then 2/9, maybe here. We're up here. And so what you can see, I believe, what's happening here is that we're compressing the sine curve. As we get closer and closer to 0, it's going back and forth faster and faster and faster and faster and faster and faster and faster. And actually, as we approach 0, it oscillates back and forth infinitely fast. Now, I think we're ready here to move on to the talk about limits. So let's start out here. Remember, in the last video, f of x was equal to x plus 2. And basically, it looked like this. As we got closer to 3, from the left to the right, the y value squeezed in on 5. So we said the limit as x approaches 3 of f of x is equal to 5. Okay, now, so graphically, our argument is something like this. If you give me a radius around 5, I can find a radius around 3 so that all of my interval values will be mapped inside your interval by the function f of x. And if for every radius you give me around 5, I can find a radius around x so that all of my values map inside there, then we say that the value at the center of the radiuses you're giving me is actually the limit. Now, a couple of things about this. These have to be open intervals. In other words, the endpoints are not included. So to get the radius around 5, there have to be some values at least on each side of 5. Okay. Now, okay, so let's imagine that in this particular case, you give me a radius of 0.01. Now, I'm going to put in parentheses here a Greek letter, epsilon, and I'll explain that later. Okay, so I can use then a radius of 0.01 as well. And I'm going to put right next to my radius a little Greek letter delta, and I'll explain that a little later. And so what you're saying is that your interval is the open interval (4.9) is less than y is less than 5.1. Oh, no, excuse me. I got 4.99 is less than y is less than 5.01. And so what I'm saying is my interval will be, what will it be? 2.99 is less than x is less than 3.01. And if you'll notice that when we apply x plus 2 to every number in the 2.99 to 3.01 interval, we get the numbers in the 4.99 to 5.01 interval. Now, it's not necessary that I hit all of the values in your interval. It's just necessary that my interval is inside your interval. So I could have used 0.001, for example, and that would have been a very more narrow focused interval inside yours. But that is basically the argument we make when we say, mathematically, when we say, as x gets closer and closer to 3, f of x gets closer and closer to 5, or the limit as x approaches 3 of f of x is 5. Now, let's state this in a formal fashion. Now, this is a definition that was proposed by Cauchy, who was a mathematician, to be a formal definition of limits. And it's really very elegant and beautiful, and it requires some meditation to really understand this definition. And I believe that it is definitely worthy of your time. Unfortunately, the AP folks and many others have decided that it's not worth it. And I think the reason they do that is because students don't take to it immediately for a lot of reasons. I think the reasons are, I think the primary reason may be that they don't understand what the definition is saying, because many students aren't well schooled in absolute value inequalities. But I'm hopeful of you guys. So now here's what we're going to do. We say that the limit as x approaches c of f of x equals L if for every epsilon greater than 0, there exists a delta greater than 0, so that whenever 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L will be less than epsilon. Whoa, a couple of things that need to be explained here. This is shorthand notation for all or for every. The upside down A is what we call the universal quantifier. It works for all. Okay, so what we're saying here is this works for all epsilons greater than 0. Any number you choose greater than 0, it's got to work. And this is the existential quantifier, which basically asserts there exists or there is at least one. Now notice, in this argument, for every epsilon greater than 0, in other words, if we're arguing together that the limit is something and I'm asserting that it is and you're trying to disbelieve me, and that's what a proof is, then you get to give me the epsilon. Okay, that was the 0.01 that was marked in blue up here. And then I choose the delta. In other words, all that has to happen is for any epsilon you give me, there is at least one delta that works. And so I chose a delta of 0.01. That's the second one with the delta. And then when 0 is less than the absolute value of x minus c is less than delta, in other words, if I have an x that's in the delta interval about c, then it will map that value into the epsilon interval about L. That's basically what it's saying. Now, obviously, if this were a proof, and you know by now that a proof is where a prover tries to convince a provee against his opposed will that something is true, and if the provee cannot oppose this logic, then it's proven. So the provee would choose an epsilon that was quite small. I mean, if you said, well, let's let the radius around the limit be 100, then it'd probably be pretty easy to map the values in. But if we said we're going to let the radius around the limit be really small, really tiny, then that would be where this argument would break down if I couldn't find a delta. Okay, now I really recommend that you spend some time meditating on that. Now, let's take a look at the case where the value we're trying isn't the limit. So the one that I want to use is the sine of pi over x. So f of x equals the sine of pi over x. Okay, and I want to claim that the limit as x approaches 0 of f of x is equal to 0. And so you give me an epsilon interval. Let's say you say, let's let epsilon greater than 0 be equal to 1/2. So what that does is that gives us, here's 1, here's -1. That gives us an interval between here and here. Now, if I come out here, I know at, what was it, what was the first value? I know at 2/5, we're up at 1. And then at 1/3, we're back at 0. So I'm going to choose, but by the way, 0 is the one I'm putting in. So I'm going to choose a very tiny epsilon interval here. Let's just let my delta interval, I'm going to let delta equal 1/100. So surely by then we'll be inside an interval here so that we won't get that. But if you look back at this chart here, if you look at the values where f of x is 1, it's 2/5, 2/7, 2/9, and so that would continue on 2/11, 2/13, 2/15, and so forth. So what about letting x equal 2/201? Now that would be f of 2/201 would be equal to the sine of 201 pi over 2, which is 1. And so even with that delta interval of 1/100th, I can't get all of the functional values to be within 1/2 a unit of 0. And if I change the delta limit to 1/1,000,000, then just 2/2,000,001 would still give me a value of 1. So there is no delta around 0 that will give me functional values that will always map to within 1/2 unit of 0. Therefore, 0 is not the limit, and that's kind of shown out by this delta epsilon definition of the limit. Okay, so I'm going to stop this video at this particular point and start another.